In this video, we'll discuss image reconstruction, CT numbers, Hounsfield units, and window width and window level in CT. Data collected by the detector in its most basic form is referred to as raw data. This data is then reconstructed into image data. Certain manipulations, such as filtering the data, must be applied to the raw data as part of this initial reconstruction process, while other manipulations like multiplanar reformatting are performed directly to the image data, which the technologist can view and manipulate visually. To reconstruct and interpret the data acquired by the detectors, the proportion of X-rays absorbed by the patient for every path from the tube to the detector must be calculated. This calculation is called the linear attenuation coefficient, the proportion of X-rays attenuated in a line from the tube through the patient to the detector. The linear attenuation coefficient is denoted with the Greek letter mu and is expressed in units of per centimeter. For example, the linear attenuation coefficient of water, denoted as mu water, is equal to 0.181 per centimeter. This means that 18.1% of photons from a diagnostic X-ray beam passing through 1 centimeter of water will be absorbed. The linear attenuation coefficient of an X-ray beam passing through a patient in the CT scanner will vary based on the thickness of the patient or the body part, the atomic number of the material, the tissue density, and the energy of the beam as defined by the KVP. This makes for a complex mathematical situation in which the attenuation pathways from all angles need to be unwoven in order to map out where in 3D space X-ray attenuation has occurred. This process of tracing attenuation back to the voxel in which it happened by calculating the linear attenuation coefficient through each voxel from various angles is known as back projection, and that process is the basic building block of reconstructing a CT image. Rather than constantly thinking and processing data in terms of complex linear attenuation coefficients, in CT scanning we use a simpler measure called the CT number, expressed in Hounsfield units. The CT number is a measure of the radiographic density of a voxel described with reference to the density of water. This means that the CT number of water is 0 Hounsfield units. The CT number of anything which attenuates more X-rays than water, blood, muscle, brain, solid organs, bone, or metal, those are all greater than 0 Hounsfield units. The CT number of anything which attenuates less X-rays than water, so fat, lung tissue, or air, is less than 0 Hounsfield units. To calculate these CT numbers, we need a mathematical way to describe the amount of attenuation relative to our 0 level reference point of water. To do this, we take the difference between the linear attenuation coefficient of our tissue, mu t, and the linear attenuation coefficient of water, mu w, divide that difference by the linear attenuation coefficient of water, mu w, and then multiply that number by 1000 to place it on the Hounsfield scale. This calculation means that the lowest possible CT number is minus 1000 Hounsfield units, and most of the body's tissues fall well below the plus 1000 level, with the exception of dense cortical bone, which can be as high as 1500 or 2000, and metal implants, which can be even higher. So now that we have this nice neat scale in a range relative to the number 0, we can use those CT numbers to assign grayscale values from black to white and anywhere in between to show those tissues in a variety of shades of gray. Once the scanner has calculated those CT numbers and performed reconstructions, the numbers themselves are constant values representing their respective voxels. But the way that we display those CT numbers can be manipulated based on our window width and our window level. Window width refers to the range of CT numbers displayed. So if we want to see every shade between black and white spread out over a wide range of tissue densities, we can use a wide window width. Conversely, if we want to see a very small range of tissue densities which are close together to the exclusion of everything else, we can use a very narrow window width. An example of a wide window width would be a lung window, with a width of approximately 1500, where we're assessing chest tissues, vessels, and their relationship with the airspace of the lungs. And because these differ very widely in density, we need to use a wide window width to distribute that scale between black and white over a very large range. Another example of this would be a bone window, where you would use a wide window width of around 1800 because there is a very large difference between the density of cortical and trabecular bone. Now on the other hand, an example of where you would need a narrow window width of around 80 would be a brain window. This is because we have adjacent structures which are very, very close in density, namely, aptly named, the gray matter and the white matter of the brain. And we want to be able to differentiate between those two tissues of very similar density to one another. So we use a narrow window width to designate a gray value between black and white to every voxel in that very narrow range, meaning that all the tissues of the brain get their own gray value and we can differentiate between them. It's important to understand that our entire grayscale between black and white is distributed across that window width. So if you use a narrow window, you're squishing that grayscale down to differentiate between similarly dense structures. And if you use a wide window, you can distribute those grays across a very distant range of densities. Any structure with a CT number that falls outside of your window will be displayed as black if it's lower than your window, or white if it's higher than your window. As well as controlling how widely distributed our grayscale is across CT numbers, we can also control where that grayscale is centered, and this center point is referred to as the window level. With window width, we're asking how close or how far apart are the densities that we're looking at, whereas with window level, we're simply asking, are we looking at high density or low density structures? If we're assessing high density structures like bone, we want a high window level of around plus 500 because we know bone has a high CT number value. If we're assessing low density structures like lung tissue, we want a low window level of around minus 500 because we know that lung tissue has a low CT number value. To combine these principles of window width and window level, any window setting for viewing a certain type of tissue will have a window width describing the range of CT numbers shown and a window level describing the CT number where that range is centered. To return to our example of the brain window, a typical brain window would have a window width of 80 and a window level of 40. This means that our width of 80, that range of 80, is centered on the number 40, and that all gray levels between black and white are displayed for the various densities between 0 and 80 Hounsfield units. And any tissue with a CT number below 0 is black, any tissue with a CT number above 80 is white. Now this is just a tidy example because it happens to land our lower edge at 0, but another example with a more intermediate window width would be an abdomen window, which has a window width of around 400 and a window level of 50. So this would mean that our range of grays will span structures with a CT number between minus 150 and plus 250. This range encompasses the various organs, tissues, fat in the abdomen to assign shades of gray to each of them, while still being narrow enough to provide some differentiation between these solid organs. And for a final example, a wide window used for bone would be that window width of 1800 and a window level of plus 500. So this means we're displaying values between minus 400 and plus 1400 as some shade of gray, and excluding any values below or above that range as black or white respectively. This centers our grayscale at a high number because we're looking at high density structures, and it spreads our grayscale out over a wide range because of the large difference between the density of trabecular and cortical bone. Some of the concepts in this video are tricky, but I really believe that anyone watching this can master these concepts as long as you can approach them and understand them from the right angle. Make use of the closed captions, playback speed, and script down below, and feel free to work together and bounce ideas around in the comments. Keep up the hard work, and thanks for watching.